We're about to start, okay?
Okay.
Okay, so welcome back, everyone. The last talk of today is by Anna Biggs from Princeton about melonic quantum mechanical model for without disorder.
Yeah. Hi, everyone. I'm Anna. I'm I'm really sorry I can't be there in person. But thank you to the organizers for including my talk on Zoom. Yeah, so I'm going to discuss a model that I was thinking about recently with Juan and Loki Lin. Um, and this is a novel holographic quantum mechanical model. In particular, it's a model of interacting fermions without disorder that has the same low energy physics as the n equals 2 supersymmetric SYK model, or in other words, it's described by the n equals 2 super Schwarzschild theory in a regime where the number of fermions is large and the temperature is low. Okay, but it differs from SYK in that it does not have disorder. Um, in particular, it involves n equals 2j plus 1 complex fermions that transform in a single spin j representation of SU2. This is a supersymmetric model. So the Hamiltonian is the anti-commutator of two fermionic operators, which are these supercharges, which involve the Wigner 3J symbol. And I'll describe the model more precisely in a minute. I should mention that models with couplings mediated by these Wigner 3J symbols have been previously discussed in the literature, first by Ahmed and Merginsky and more recently by Bendetti and Delporte, which inspired this work. So these were field theories, bosonic field theories with couplings mediated by these symbols. Um, Now, before I define the model more precisely, let me give some motivations for why we were interested in studying it. A big motivation is that this model exhibits a novel mechanism for a so-called melonic expansion. And if that word is unfamiliar, I will review what it means, but it's important because when a theory is melonic, you can resum all of the Feynman diagrams and compute correlation functions at strong coupling. So we've basically understood a new class of models that we can solve at strong coupling. And as I mentioned, this is a holographic model in the sense that it has an effective action in a particular regime, which is given by the n equals 2 super Schwarzschild. And so therefore it has a holographic interpretation as describing the near horizon excitations of certain near extremal black holes in supergravity, as well as their BPS microstates. And so if you are interested in understanding the characteristics of those microstates, such as the extent to which they exhibit some kind of chaos or the fortuity mechanism, this is an interesting solvable toy model where you can start to investigate some of those questions. Um, because the coupling is a 3J symbol, it also bears some resemblance to what you would get from reducing a field theory on a sphere. For example, ABJM in the presence of a magnetic field. Um, and so you could view this model as a kind of solvable avatar for those more complicated things that you would get from such a reduction. Um, it's also amenable to exact diagonalization. So you can solve it exactly on the computer for relatively small values of n. And I'll discuss or present some of the results of exact diagonalization later in the talk. And then another interesting property of this model is that in a sector of large SU2 charge, the model simplifies and becomes equivalent to a 2D CFT. Okay. And I'll explain why that is. If there are questions, also please just interrupt me. Okay, so here's just a bare bones outline of what I plan to discuss. First, I'll define the model and discuss some of its basic properties. Then I will explain why it has a melonic expansion, and discuss the regime in which it's described by the Schwarzschild action, which is related to this melonic expansion, the fact that it emits a melonic expansion. Then I'll explain the regime where the theory is described by 2D CFT. And if I have time, make some comments about the BPS state counting problem. Okay. So as I mentioned, this model involves 2J+1 complex fermions, which transform in a single spin J representation of SU2. So this M here runs from -J to J. These fermions obey the canonical anti-commutation relations. The supercharge couples these fermions through the Wigner 3J symbol, which describes angular momentum addition. So in case you forgot the definition of the 3J symbol, it's basically the SU2 Clebsch-Gordon coefficient. Here, this J is a coupling with units of energy, dimensional coupling like we have in SYK. I'll use this font for J to denote the coupling, as opposed to the SU2 generators, which will come later. So there's a lot of J's floating around. And in this definition of the supercharge, we take this little j always to be an odd integer, because for odd j, this 3J symbol is anti-symmetric in the indices. Okay. N and little j are both counting the number of fermions, so I'll use them interchangeably. Okay. We can also express the Hamiltonian in this form. This is the normal ordered form. And in this form of the Hamiltonian, you can see that it's a quartic interaction, similar to what we have in SYK. This operator is basically coupling two fermions into a total spin J channel. Okay, and let me mention that there's a simple way to write the Lagrangian, in which the interaction is cubic in the fields, and that's if we introduce some complex bosonic fields, which are basically composites of these fermions, in order to linearize the action of the supersymmetry transformations. Okay, so these are some auxiliary bosonic fields, and in terms of those fields, the Lagrangian can be expressed in this way, which is cubic in the fields. And I mention this because I will use this interaction when discussing Feynman diagrams later in the talk. So the Feynman diagrams will be cubic in the fields. Now, this model has some charges. So there's the R charge, which is basically proportional to the fermion number. So here we've defined the fermion number with this relative shift so that it's charge conjugation symmetric. And then the R charge is proportional to the fermion number, normalized so that the supercharges have R charge 1. There are also SU2 currents, because the model has this SU2 symmetry. So we have J3, which is, you can think of as the projection of the angular momentum in the Z direction, and J plus and J minus, which move us between sectors of fixed J3. Okay. Now, this model is a model in 0 plus 1D. It's a quantum mechanical model. But there's another convenient way to view the Hilbert space, which I want to mention now because it will provide some intuition for some of the physics. So we can view these fermions, psi m, as the modes of a 2 plus 1 dimensional fermion moving on a two-sphere cross-time, where the two-sphere encloses a magnetic monopole with n units of magnetic flux. So this system, if we look at the lowest energy sector or the lowest Landau level, we would find that it is n-fold degenerate and transforms in a spin J representation of SU2. So that's the same Hilbert space as we have in this model. And this is another way to view where this Hilbert space is coming from, basically. Okay. In terms of this perspective on the two-sphere, in the large J limit, we can think of wave functions as some coherent states localized within one flux quantum on the sphere. So, in other words, a spin J representation of SU2 can be treated as a classical spin in the large J limit. For example, if we have some wave function sitting at a direction n hat on the two sphere, this would have angular momentum J n hat. Okay. So I'm talking about these wave functions again on the two sphere in some coherent state representation now. And we can think of this as something close to a basis in the large J limit if we take these wave functions as approximately uniformly distributed over the sphere. Now, to continue with this two-sphere picture for a moment, I want to mention an important set of states. And these are the states which have the largest possible J3 eigenvalue. So those are states where we fill the two-sphere with fermions whose angular momentum is pointing up as much as possible so as to maximize the J3 eigenvalue. So in other words, we fill the whole northern hemisphere. In terms of the fermionic modes that we started with psi m, this corresponds to filling all of the states with positive m. There are two such states because the m equals 0 fermion does not contribute to the J3 eigenvalue. And the J3 eigenvalue of these states is proportional to J squared. So that's the sum of m from 1 to J. Okay. Now, those were the states with the largest possible J3. We can discuss more generally how all of the states break down by their J3 eigenvalue. Here, I've plotted the distribution of states by J3 eigenvalue for some various values of little j. But the main point I want to make here is about what this distribution looks like in the large J limit. So at large J, we can do a saddle point approximation to this distribution. And now I should maybe say explicitly this m is denoting the J3 eigenvalue. Okay. When we do this saddle point approximation, the distribution of states by J3 eigenvalue here has some Gaussian profile, and in the regime where J3 is very large, the density has the form of a Cardy density of states for a 2D CFT. The states, the hemisphere states that have the largest J3 eigenvalue, which we were just discussing, are on the ends of this distribution. So I'll give a more intuitive explanation for that later. But I just want to give a picture of what this distribution looks like. So far, in the plots that I've given here are just a consequence of SU2 representation theory. All I'm discussing is the Hilbert space. Perhaps more interesting is the distribution of BPS states by J3 eigenvalue. Now this has something to do with our Hamiltonian. And like n equals 2 SYK, this model has a large degeneracy of supersymmetric ground states, or BPS states. So here the BPS states are those which have exactly zero energy, are annihilated by Q and Q dagger. And we can use Witten index arguments to count these BPS states by their J3 eigenvalue. So in total, there are exponentially many states in J, 2 times 3 to the J, BPS states. And similar to the distribution of all of the states, the degeneracies of the BPS states by J3 eigenvalue have a similar profile. So in the regime where J3 is order 1, they have some Gaussian profile. And in the regime where we are near the maximum value of J3, they have some Hardy-like profile. Here I'm plotting the logarithm of the state count by J3 eigenvalue, and comparing all of the states to the BPS states, as well as showing their these Gaussian and Cardy approximations that I mentioned. So this is all of the states. These are the BPS states. And mostly what I want to point out here is that the two hemisphere states with the largest J3 eigenvalue are actually BPS. So those states are always BPS. And moreover, the BPS states have all possible J3 eigenvalues. So they transform in all of the spin J representations that we get in this multi-particle Hilbert space. Okay, so far I've just been discussing the model and its symmetries and some state counts. Now I am going to move on to the discussion of the melonic expansion. Okay. So the goal here is to basically try and give some intuitive explanation for why this model has a melonic expansion. First, let me give a little bit of background about why we care about this. So in some field theories and quantum mechanical models, a subclass of all of the Feynman diagrams, which are nowadays called melon diagrams, have the dominant scaling in n. So here, in our case, n is the total number of fermions. In a field theory with cubic interactions, these are some examples of melonic diagrams. This is a melonic correction to the propagator. This is a melonic vacuum diagram. And this melonic expansion is desirable because it means that you can sum all of the Feynman diagrams in the large n limit and thereby compute correlation functions at strong coupling. So the subclass of Feynman diagrams that are left when we look at the dominant scaling in n can be resummed, basically. And SYK is one example of a model with a melonic expansion, which is part of the reason why it's so popular. But in SYK, the origin of the melonic expansion has to do with doing a disorder average over the couplings. In this case, we do not have any disorder average. Our couplings are fixed. But the same melon diagrams dominate in the large n limit, however, for a different reason than in SYK. So now I will try to describe what that reason is. I should mention that in the past, bosonic field theories with cubic interactions given by these SU23J symbols were studied, as I mentioned at the beginning. And there the authors also argued that the melon diagrams dominate. using facts about the large J scaling of SU2 invariants, so the 6J, 9J, 12J symbols, etc. But the general asymptotics of those invariants is an open problem. So in those papers, they did not prove melonic dominance, but they checked it basically up to a large number of loops. Here, we hope to give a more intuitive argument for why we expect the melons to dominate at all orders. Okay. So at large J, the 3J symbol enforces classical angular momentum conservation. So in other words, at large J, if we are again thinking of the coherent state representation of these wave functions, the angular momenta of the fermions, which is proportional to the vector n hat, the direction that wave function sits on the two-sphere, those three vectors must sum to 0 in order for the 3J symbol to have support. That's the sense in which it enforces classical angular momentum conservation. Okay, and this equation should hold at any vertex. So in particular, since these three vectors are all on the two-sphere or on the unit sphere, they all have the same length. And this means they have a relative angle of 2 pi over 3. But they can still be rotated inside the sphere. These vectors can still be rotated inside the sphere. So this is the picture of the interactions that we have at large J. And with that in mind, let's consider the simplest melon correction to the propagator. Okay. So if we fix the vector corresponding to this propagator, n1, we have some degeneracy of possible configurations for n2 and n3 on the two-sphere. So fixing n1, n2 and n3 can be rotated inside the two-sphere while still satisfying the angular momentum conservation condition. And so there's a circle's worth of degeneracy of solutions to that equation. For this diagram, what that means is that there is an enhancement proportional to the total number of states swept out by this rotation. And the sphere area scales as n, which means that this circle contributes a factor of square root n. Okay. The area scales as n because n was the magnetic flux through the sphere. Okay. Now, let's consider the following two corrections to the propagator. This is a melonic correction, and this is a non-melonic correction. We can use the overall rotational invariance of the two-sphere to fix the first three arrows. So once we've fixed this, and this, all of the remaining red lines have been fixed. The arrows corresponding to those propagator lines have been fixed. Okay. Now, on the left, we have freedom to rotate the arrows inside this bubble that we just discussed. Okay. On the right, we don't have the same freedom. In other words, if you were to solve the angular momentum constraint equations corresponding to these vertices, they would admit only a discrete set of solutions, while here we would get a continuum of solutions. One way to see that is that on the right, all of these unfixed arrows share two vertices with two different fixed arrows. while here, all of the unfixed arrows share two vertices with the same two arrows. And so basically, one of these constraint equations is redundant. That's where the extra moduli is coming from. So the conclusion of this analysis is that the non-melon is suppressed relative to the melon by a factor of square root n. Okay.
That's a good question.
Yes, please.
So in the conventional, like the hope large n limit, you can also organize the like leading and subleading ones by some genus expansion, right? Do you have some understanding here of like can you classify them into, leading is melon and then what's subleading and subleading and so on?
Yeah, that's a good question. We didn't try to do that. So I guess the analogous statement would be, at least the way that I in practice understood the scaling of these diagrams was, given some diagram, you can use some facts about SU2 recoupling to break a given diagram down into the melonic contribution and then some SU2 invariant, 6J, 9J, 12J, blah, blah, blah. And then to determine the scaling of that invariant, you would, so the scaling of the melon diagrams. To determine the scaling of the invariant, you would write down a fully melonic diagram with the same number of vertices, and count the difference in the number of moduli. Yeah, but I mean, it would certainly be very interesting if there was an interpretation of these diagrams, the vacuum diagrams, for example, as triangulating some surfaces, maybe some 3D surfaces. But that's not something that was clear to me.
Thank you.
Yeah. It's true that the tetrahedral diagram, for example, which corresponds to the 6J symbol, has some interpretation as the volume of a tetrahedron, which has been studied, known for a long time. Spin foam gravity literature, but that doesn't it doesn't seem like that's the right interpretation for this model, because here the melon diagrams are really the ones that correspond to gravity, and the 6J symbol would be something that's subleading. So anyway, yeah, thank you. Are there any other questions? Okay, please interrupt me if there are. So we can give a basically more general counting argument for all of the vacuum diagrams, which basically goes as follows. So each line corresponds to a point on the two-sphere, and so it contributes two free parameters. So here the goal is to count the number of free parameters in a general vacuum diagram. Each line corresponds to two free parameters. Each vertex imposes three constraint equations because it's a vector equation in 3D. Now, you can check that if angular momentum conservation is obeyed at all of the first n vertices, it will be automatically obeyed by the last one. So we have really one fewer constraint equation relative to the total number of vertices. And for a general vacuum diagram with cubic vertices, the number of lines and vertices are related by 2L equals 3V. So the number of free parameters that we expect for a general diagram is twice the number of lines minus 3 times the number of vertices minus 1, which is equal to 3 using this relation. And these 3 degrees of freedom are basically corresponding to the rotational symmetry of the problem. So you can get rid of these 3 degrees of freedom by fixing the overall rotation of all of the arrows. So the conclusion of this counting is that a general vacuum diagram does not have any free parameters. Then, as we alluded to before, the melon diagrams basically have redundant vertex constraints. And so they are an exception to this counting that we just did. In particular, we get 1 free parameter per pair of vertices. So that was an explanation of why we have this melonic expansion. And one consequence of the melonic expansion is that the Feynman diagrams that survive in the large N limit are the same as those in n equals 2 SYK. And therefore, the Schwinger-Dyson equations are also the same. And so if one analyzes the Schwinger-Dyson equations, as have been done in SYK, this means that in the IR, the model has an approximate conformal symmetry, and the effective action, which gives the leading corrections away from the conformal limit, is the super-Schwarzschild action. This is interesting to us because SYK has a holographic interpretation, as I mentioned, as describing near-horizon excitations of near-extremal black holes in supergravity with an ADS2 throat. But one advantage of this model relative to SYK is that the couplings are fixed, so it's sort of a step closer to the examples of holography that we expect to be a little more realistic. Now, one thing I want to mention is that a new feature of this model compared to n equals 2 SYK is that it has a global internal SU2 symmetry. And we would expect some low action degrees of freedom from this symmetry. Ordinarily, if we had some SYK model with an internal SU2 symmetry, one would expect that the low energy action corresponding to that SU2 symmetry is the usual sigma model action, where this G is an SU2 group element. But it does not appear that this is the correct answer in our case, because as I mentioned, the BPS states live in all different SU2 representations. In particular, they live in large SU2 representations. However, this action would raise the energy of modes with non-zero angular momentum. And so it would not be consistent with the BPS spectrum that we have. One guess, which we did not derive, but in principle could be checked, is that the action instead contains a first-order term of this form, where now rho is a new field whose components transform in a triplet of SU2. And in this action, there's in this hypothesis, there's no other action for rho. Okay. So this is sort of like the group valued analog of PQ dot. It's there to give the correct quantized Hilbert space, but it doesn't contribute any energy. Okay. So that was a discussion of the melonic expansion and the Schwarzschild regime. Now I want to discuss a different regime, In particular, one where we look at states with very large SU2 charges. And I mentioned in the beginning that in this limit, the model simplifies and becomes closely related to a 2D CFT. So I'm going to try to explain why that is. First, I'll give some physics intuition for why we might expect a CFT, and then I'll try to be more precise. So let's consider, again, the states with the largest possible J3 eigenvalue that correspond to filling one hemisphere, and look at excitations around those states. So this is a quantum Hall-like system where we have fermions in a perpendicular magnetic field. And in such a system, you would expect gapless chiral edge modes on this equator. So for small excitations around these filled hemisphere states, the Hilbert space looks like what you would get for a 1+1D chiral CFT. Now, in general, if you introduce some local quartic interaction between the modes on the equator, these edge modes, you would still expect some kind of chiral CFT. One concern you might have is that our interaction on the equator really looks non-local. But the idea will be that we can view this as local if we appropriately rescale the size of the circle. So in other words, if I do a Z3 quotient of this circle with the appropriate boundary conditions, what looks like a non-local interaction on a larger circle becomes local, but on a smaller circle. Okay. I want to emphasize that in this regime where we are considering excitations around these maximum J3 states, this is not a regime where the melonic approximation is valid. In particular, the melonic approximation relied on being able to rotate two of the arrows when one is fixed. But here, this interaction is confined to the equator. So we don't have the rotational freedom that was required for that melonic expansion. So this is a regime that's separate from the Schwarzschild regime, which is valid when we're looking at states with relatively small J3 eigenvalues. Okay, so now I'm going to describe this 2D CFT more precisely. If we write down our supercharge and use an asymptotic expression for the 3J symbol in this large J limit where the m's are small compared to J, you can show that the supercharge takes this form, where now this psi is a single fermion in 1+1D, which is living on the equator. The psi n that we started with correspond to the momentum modes of this psi around the equator, around this circle. And here I'm using phi to denote the coordinate on the equator. So in this limit, the supercharge basically corresponds to a non-local interaction of a 1+1D fermion separated by 2π/3 on the circle. Okay. And based on the pictures that we've been drawing, perhaps it's also evident that this is the correct form of the interaction in this limit. Now, we could continue to describe the 2D CFT in terms of psi, but it will turn out to be simpler if we bosonize the fermion. So if we write psi equals e to the I phi, then the supercharge becomes the integral of the exponential of this boson phi evaluated at points separated by 2π/3 on the circle. And this turns out to be simpler because now Q only depends on the momentum modes of phi, which are integer multiples of 3. So in other words, if we take this linear combination of phi, expand in momentum modes, we would find that only those which are 0 mod 3 are non-zero. And so if we rescale the size of the circle, as we mentioned before, we can just view this as a single boson defined on a smaller circle. So this becomes the ordinary momentum expansion of a single boson. Yes? Okay, I thought maybe there was a question. Okay, and I will call this boson phi z. Now, in terms of phi z, if we compute the Hamiltonian, we just get the free kinetic term for this boson phi z. And this is expected if you happen to know that the form of the supercurrent at the n equals 2 superconformal point of the CFT of a single boson has exactly this form, which is the form that we had for our supercurrent here, the exponential of a boson. Then you know that the stress tensor will just be d phi squared, and the U1 current proportional to d phi. Okay. So in this regime, the Hamiltonian of our model, to summarize, is just that of the free boson phi z. So now we see why it was a little bit simpler to bosonize. Okay. So we might be wondering, okay, the Hamiltonian only depends on phi z, but we also had the momentum modes, the other momentum modes of this original boson phi, those which were plus or minus 1 mod 3. Okay, so where did those go? We can write this 1 plus 1d boson as a sum of 3 terms, where these 3 terms are phi z, which we just discussed, and then phi plus and phi minus, which correspond to the momentum modes, which are plus or minus 1 mod 3. And when we move to the smaller circle, so when we rescale the size of the circle, the phi z will be periodic, but phi plus and phi minus will have some twisted boundary conditions based on being plus or minus 1 mod 3. The important point is that phi plus and phi minus don't appear anywhere in the supercharge of the Hamiltonian. So they don't contribute anything to the physical energy of the model, which only depends on phi z. But they do contribute to the J3 eigenvalue. Okay, so why is that? Well, if we were to rewrite J3 in terms of these bosonic fields, we would find that the difference from the maximum J3 eigenvalue is the sum of these 3 kinetic terms. One way of seeing this is to recall that the expression for J3 in terms of the psi m had this form here, which in terms of the 1 plus 1d boson on the equator has this expression, which is the free kinetic term for the 1 plus 1d fermion, and then when we bosonize, we get the free kinetic terms for these bosons. So excitations of phi plus and phi minus change J3, but they don't change the energy. And this, I'm emphasizing this because it will give a very simple expression for all of the states, and in particular, the BPS states of the model. So to summarize, the Hilbert space we can view as the Hilbert space of some decoupled chiral CFTs, where we have one factor describing phi z, and then another factor describing phi plus and phi minus. Okay. Now, I mentioned that this understanding gives a very simple expression for the BPS states in this limit. And that's for the following reason. So the states, the hemisphere states that we've been discussing with the maximum J3 are always BPS, and we are thinking of these as the CFT vacuum. Now, we get all of the other BPS states by starting from those 2 states and adding the oscillator modes of the phi plus and phi minus bosons while staying in the zero energy state of phi z. So acting with phi plus and phi minus changes J3, but it doesn't change the energy. And so we simply generate all of the BPS states by acting with the oscillator modes of these guys. And this explains why the count of states by J3 eigenvalue that we discussed at the beginning has the form of a Cardy density. In particular, why the BPS state count has the form of a Cardy density near J3 max. The partition function, which counts the BPS states in this large in this regime, in the CFT2 regime, is simply the BPS state partition function of a free boson where we've only kept the modes that are plus or minus 1 mod 3, because those are the counts corresponding to phi plus and phi minus. Okay, so here is a graphic of what I just explained in words. We have these CFT vacuum states, of which there are 2, and we get all of the other states with lower and lower values of J3 by acting with phi plus and phi minus. Okay, now I want to comment on some of the compare the Schwarzschild and the CFT regime, and then I'll make some comments about the BPS states beyond the CFT regime. So the CFT regime is it's interesting that the model simplifies so much in this limit, and it's also completely solvable. And well, we can describe the BPS states explicitly in this limit, but it does not obviously have any gravitational interpretation like the Schwarzschild regime. And so it's interesting to ask how the model interpolates between these two regimes. And in fact, they have some features in common. So the 2D CFT predicts lowest energy for a given R charge. So these are states with no phi Z oscillators excited, but with some momentum and winding. And that's given by this expression here. Separately, the Schwarzschild action predicts a gap between the BPS and non-BPS states. So the gap between the BPS and the first non-BPS state, which has this expression here. And these two expressions don't need to agree, and indeed they don't in detail. But we see that they're both quadratic in R for large R and scale as 1 over n, which is a curious fact about the energy spectrum, that the gap scale is roughly the same. Also, if we take the Cardy density of BPS states and just naively extrapolate to the regime where J3 is small, then we get the correct J dependence in the exponent, as would be predicted by the Schwarzschild result. So the log of the number of BPS states scales as J. Similarly, the entropy of the non-BPS states has the correct J and E dependence compared to the Schwarzschild answer. So the CFT predicts that it scales like square root of J times E, okay? So some aspects of the counting are correct, even though the physics is quite different. An important difference between these two regimes is that the non-BPS states are highly degenerate in the 2D CFT approximation, while in the Schwarzschild description, they should form an approximate continuum. And so basically, we expect that those degeneracies will be increasingly broken as we move to smaller and smaller J3. Here I have some results of the exact diagonalization to illustrate this point, and also to illustrate that we can really solve the model on a computer. So I'll just go through this relatively quickly. So here we are plotting the energies of the states by their R charge. in a model where J is equal to 11, and we're plotting only a subset of all of the states with relatively large angular momentum so as to compare with the CFT prediction. So this L is the SU2 representation that the spin transforms in, or that the state transforms in. This pink is the prediction for the lowest energy state in a given R-charge sector. And these green dots are the states with the largest J3 for a given R-charge. So the largest J3 in a given R-charge sector depends on R. And you can see that those agree quite well with the CFT prediction. I want to focus in on some clump of states. So these states are roughly clumping around the CFT predictions, which is illustrative of the degeneracy that we expect in the CFT regime. So let me just zoom in on this clump of points here and plot their distribution by SU2 representation. So that's what's shown on the right-hand plot here. This pink plus is the CFT prediction, and the green point is the state with the largest J3 in this R-charge sector. The point I want to make is that in the CFT approximation, all of these states would be degenerate with this one. However, since we are doing a numerical finite J calculation, that's breaking those degeneracies, and the degeneracy is increasingly broken as the SU2 representation decreases. Okay. So as we move away from the CFT regime, what initially are some highly degenerate energy levels become more and more non-degenerate and chaotic, as we would expect. Okay, here I'm also plotting the comparison of the lowest energy non-BPS state to the gap scale predicted by the Schwarzschild, which, and you can see that as we increase J, which is the N in our model, those energies are converging to the Schwarzschild prediction. Okay, so with the time I have left, I want to comment on make some comments about fortuity and then the BPS state counting problem beyond the CFT regime. So there's been interest in classifying BPS states as fortuitous or monotonous, as I think has also been discussed at this conference. And at large N, these fortuitous states are supposed to describe black hole microstates. Now, there have been classifications of fortuitous and monotonous states for similar models to this one, such as n equals 2 SYK. And by those classifications, all of the states in this model would be called fortuitous, basically because they exhibit this R charge concentration feature, which is that nearly all of the BPS states have a particular value of the R charge. Now, the BPS states that we just discussed in the CFT2 regime are obviously highly ordered, and they have a simple description in which they're BPS for every value of n. So qualitatively, they behave much more like the monotone states of n equals 4 super young Mills. The BPS states, which we would expect to behave like black hole microstates, are those for smaller values of J3, where the Schwarzschild description is valid. And there we don't have an explicit description of those states. So one conclusion is simply that this the fortuitous monotone classification that currently exists is not a good metric, at least in this model, for distinguishing black hole microstates from non-black hole microstates. Now, although we don't have an explicit description of the BPS states in the regime where we expect them to behave like black holes, we can count them. So I mentioned that we can write down the BPS state partition function in the CFT2 regime in this way. This 2 is related to the 2 BPS states that we started with, which can be re-expressed in this form. And using Witten index arguments, we can also write down the BPS state partition function for the full model, which is related to, has a very similar form to the one in the CFT regime, except that we have a cutoff here given by J. So this CFT2 is in some sense an infinite N approximation to the finite J theory. Okay, and we can wonder how much we need to decrease J3 from the maximum value before the counts given by these 2 partition functions start to differ. Okay. Now, one can show that the first correction appears when we lower J3 by an amount J, which corresponds to the following qualitative picture. So starting from this hemisphere state, if we consider single particle excitations of this vacuum, this corresponds to adding a hole or a fermion. And let's continue with the hole scenario. If once this hole reaches the south pole of the sphere, it realizes that the Fermi sea is not infinitely deep. And it realizes that this infinite N approximation that we're working with in the 2D CFT is just an approximation, right? So this hole, once it reaches the South Pole, has lowered the J3 eigenvalue of the hemisphere state by J, which is why we see the first correction once we lower J3 by J. Now, let me mention another way to express this fact, which makes the comparison to trace relations in n=4 more manifest. So we can rewrite the finite J partition function in terms of these bosonic oscillator modes in this way here. And once we've written it in terms of the bosonic oscillator modes, we get this factor in the numerator, which are basically some wrong sign modes that once we lower J3 by an amount of order J will start to kick in and decrease the counts of this finite J partition function relative to the infinite J partition function. Now, although this first occurs when we lower by an amount J, the entropies don't significantly differ until we lower by an amount of order J squared, which is analogous to what we would find if we consider the energy of BPS operators in n=4 and the effective trace relations on the entropy. So in conclusion, these finite N effects are clearly important for describing the BPS states in the Schwarzschild regime, which is consistent with our expectation that those are the states that behave like black hole microstates. Here I'm returning to this plot of the entropies just to illustrate that the difference between the Cardy approximation and the true entropy really starts to occur when you lower J3 by an amount that scales as J squared. Okay, so I want to mention some generalizations of this model, which we would also expect to have some melonic expansion. I'm almost done here. So here we discussed a particular model, but I want to emphasize that the same picture in terms of the arrows that explained why this model had a melonic expansion would also imply that many other types of models have a melonic expansion. So one simple generalization would be to allow these fermions to transform in different angular momentum representations, where J1, J2, and J3 are here all large. The same arrows picture that suggested our model, or that explained why our model has a melonic expansion, would apply here, except that the arrows would be different lengths and the angles between them would not all be the same. And the same argument would go through as long as these J's are not coming close to saturating the triangle inequality. So in other words, as long as when you fix one leg, you have some degeneracy of angular momentum conserving configurations for the other two. We could also consider non-supersymmetric models, which have this form. So our Hamiltonian also had this quartic interaction, but it happened to be supersymmetric. We would expect the same type of behavior if we just have this quartic interaction and allow the fermions to transform in some different SU2 representations, but the model need not be supersymmetric. Another simple generalization would be to change the group, say from SU2 to SUN, and consider representations with large quantum numbers or large Dinkin labels. Now, let me... Yes, yes.
But can you also generalize to any odd J symbol?
Could you say the last part again? Can you generalize?
Well, I mean, to make more to put an odd number of fermions on the right side. You could,
does it need to be an odd number? Is that what you're asking, or?
Well, no, it has to be odd because you want Grassmann on supercharge, no?
Yeah, so in our case, the number of fermions was odd so that the symbol would be antisymmetric. If it was even and all of these J's were the same, then the supercharge would just be 0. Here, if these J's are different, then there's generically some phase when you swap two of these indices. So I don't think, yeah, there would not be the same restriction on even or oddness if we had different J's here. Was that the question? I may have not heard it.
I think the question was whether you can generalize to other odd numbers beyond 3, like 5J.
Yeah. Yeah, so I guess if we took here we're basically taking 2 spin J representations and recoupling into a third spin J representation, but we could ask about more general recoupling schemes, let's say. So you couple 2 spin J's and then a third and then a fourth, and you would get some, yeah, I agree, you would get some SU2 invariant. I think the only difference would be, well, one difference would be that it would not be a unique invariant. So if we consider a recoupling of 4 or 5 fermions, we won't have a unique invariant tensor. That may, yeah, so you would have to choose which one you want to use. It may be the case that at large J, all of these invariant tensors are the same, that they behave, that basically because of the angular momentum conservation, they behave in the same way. That would be my guess, although I don't know that for sure. But yeah, but I think in principle you could have a large Q, so to speak, generalization of this interaction.
Thank you.
Yes, yeah. Okay, and let me briefly comment on some other future directions that I think are interesting. So, well, this black hole microstate question we discussed a little bit already. Basically, it would be, you know, in principle, you could write down an explicit description for the BPS, for all of the BPS states, given that this model has fixed couplings, which is different from n = 2 SYK. there's some, I think, philosophical tension, at least in my mind, as to whether that should be possible or because they are expected to be chaotic. So, in other words, if the microstates that behave like black holes are very chaotic, it should probably be very difficult to write down a closed form expression for them at a general J. But in principle, it is possible. So that would be interesting to understand better. It I I think it would also be interesting to understand whether there are other theories to which this understanding of the melonic expansion to be applied. Does it allow us to solve any other theories that we care about? And finally, it was suggested recently that wormhole contributions to the gravitational path integral may be computing some kind of average over n in the boundary theory, provided that the theory admits some analytic continuation in n, which is a relatively strong assumption. And this is a natural holographic toy model with a parameter n, which we can attempt to analytically continue and see if it makes sense. Thanks a lot for your attention.
Any other questions? Yeah.
What would it mean to have the analytic continuation in N that you just mentioned?
I'm having a hard time hearing some of the questions that are further away. Sorry.
The question was, what would it mean to have analytic continuation in N?
Yeah. Yeah, I think well, the first problem is that if you have an SU2 representation for J, which is not integer or half integer, there are no unitary representations. So, and I think there are different things you could mean by an analytic continuation. Part of the question is to what extent does this still look like a reasonable quantum theory when n is not an integer? It may be that you have, let's say, many negative norm states, which appear when n is not an integer, but you can still compute correlation functions as an analytic function of n. And maybe those negative norm states become less and less coupled to the theory as you get closer and closer to an integer value of n, for example. On the other hand, it may be that the theory only has some meaningful analytic continuation in n when n is large, for example, like in the large n limit, because that's the regime in which we would expect gravity to be a valid description anyway. And so if the goal is to describe, is to explain some features of gravity, then perhaps this analytic continuation only makes sense at large n and not at small n for some reason. Yeah, what I'm hoping for is some way of defining the entire theory as a function of n for general n, and a way of computing correlation functions that reduces to the answer we would get when n is an integer. That's what I mean.
Thank you.
Mm-hmm.
Other questions? Okay, I don't see any other questions. So thanks again, Anna.
Thanks a lot for your attention. Well, I hope you have a great rest of the conference.
Thank you.